Right. Hello everyone, my name is David Evinshteyn. I'm here representing Drexel University Space Systems Laboratories as well as AI Solutions in our analysis of potential for Venus-bound CubeSat scientific investigations. So the point of our design was to analyze if a CubeSat were to deliver itself to a Venus orbit, what is the potential for scientific studies that can perform there on available instrumentation. So at the Drexel Space Systems Laboratory, our goal is to mitigate three of the biggest challenges in the interplanetary spacecraft industry, those being risk, budget, and launch opportunities. So just last year, NASA rejected the proposals of VERITAS and DAVINCI Venus spacecraft, which were competing against spacecraft in a completely different, bound for completely different celestial bodies. And eventually, these programs had to be delayed because they lost out to Lucy and Psyche, bound for asteroids. That meant that a lot of the questions that they were aiming to answer at Venus have to be delayed for future missions, of which the timing is indeterminate. Additionally, Akatsuki recently, on its way to Venus, suffered a partial engine failure and almost risked the entire mission. And due to the genius of the JAXA team, they're actually able to make it with slight delays and continue their mission and complete it. But they almost lost very valuable spacecraft on the way. Finally, in terms of launch opportunities, just this month, as we know, NASA launched the Marco CubeSats bound for Venus. However, those were a secondary payload aboard the Mars InSight Landing mission. That means that they didn't have the Delta V requirement to get themselves there, and as a matter of fact, had to hitchhike their way there. Additionally, they will not be achieving Mars orbit, as I understand it would be simply a flyby mission. So, if we want to get to Venus independently, we recognize the need for a CubeSat that lowers costs, has a higher risk tolerance, and provides us with more launch opportunities. We've been working on the design for a 12-unit CubeSat that we call TUCAN, or 12-unit CubeSat astronautical navigator, which limits us, as you know, to less than 24 kilograms in mass and a 20 by 30 by 20 centimeter frame. So what can we do with that sort of design? First of all, we've shown that the production, validation, and launch costs are significantly less than having a mission to Venus as previously done before, and also compared here to the Marco mission costs, which includes the cost of the launch vehicle as it was required for the sake of the mission. So our aim is to have an independent solution, meaning it can travel to Venus after deployment in a low Earth orbit as a secondary payload, and hope that the costs would open this platform up to private research groups and universities. So how do we take our first step in making sure that the TUCAN could reach Venus? AI Solutions provided us with FreeFlyer software, which they developed an algorithm for, in order to demonstrate that a low-thrust CubeSat with the following thrust parameters, which I'll discuss further on, is capable of making it to Venus. Our target orbit parameters were a roughly circular orbit of 4,000 to 6,000 kilometers altitude, with polar inclination for the sake of mapping, and projected to be stable enough for a decent amount of period for scientific observation with the selected instruments. Now, transferring via electric propulsion to Venus from a low Earth orbit would take about 6.5 years, as shown by the analysis, and approximately 12 kilograms of propellant. The 0.5 kilograms left over would be suitable for about 1,000 meters per second delta V, which is useful for course correction or orbit manipulation once arrived at Venus. The analysis was performed by a three-step algorithm, which first backward propagates from our desired Venus orbit until we achieve the appropriate Venus rendezvous conditions. From there, it analyzes a transfer trajectory spiraling in from Earth orbit to a Venus rendezvous, and further on iterates the Earth escape parameters necessary to minimize the delta V and find the best possible trajectory for this. For some visual representation of FreeFlyer doing its work, on the left you can see a percentage of our Venus rendezvous matching orbits. In the middle, is the interplanetary transfer. You see it nearly takes 360 degrees just to achieve Venus's orbit. And in the green on the right here, you can see our Earth escape orbits. So now that we know it can make it to Venus aboard a 12U platform, what can we fit on board? Can we make an operational CubeSat that can survive the Venus environment and perform scientific investigations there? Now, a big part of our project was to maximize commercial off-the-shelf technology aboard this design in order to keep costs low and make the mission platform more flexible. To begin, I'll talk about, as I mentioned, the ion engines we selected. So we want to use radio frequency gridded ion thrusters on board, running on an iodine propellant. We can't use the industry standard of xenon because, as our FreeFlyer analysis showed, the density necessary for xenon to achieve that delta V would exceed CubeSat pressure tank limitations. As a result, we went with solid iodine. And why did we select 2 engines on board? For the sake of our transfer periods, to minimize the time it takes to escape Earth and transfer between the planets, and all, in order to actually achieve a Venus capture, we needed the better thrust provided by using 2 orbits. In addition, they help with flywheel desaturation and attitude control along the journey, and provide redundancy in the case of single engine failure or degradation. For the power system concerns, we've selected the following solar panel configuration, as you can see there. This provides just over half a square meter of solar cell area, which translates to around 200 watts when escaping Earth orbit, going up to 380 watts at Venus. And this would be supplemented by a 57 watt-hour battery on board, and the end power distribution would be as shown here, with, of course, the majority going to the propulsion system in order to do our extended burn periods. Now, the Venus power distribution would be as follows, with a majority of it designated to the communication system, for reasons which I'll discuss further on. A good chunk now dedicated to cooling to allow it to survive in the Venus environment for a maximum period of time, and of course with some designated to the instrumentation. For onboard processing, we selected processors based on radiation resilience, as a low Earth orbit escape means passing through the Van Allen belts, so we have to make sure computer instrumentation survives this period, and low power costs. Selected here, the parameters shown are from an OM9 architecture, which we use as a general model for analysis, but hope to upgrade as better options hit the market. And we would have a 3 microcontroller configuration running in parallel for the processing needs of the CubeSat. Finally, communications were a very big challenge from Venus, as not a lot of solutions exist which allow high data transfer rates. We settled with an extending parabolic dish to maximize gain. This would roughly translate to, if we're using a deep space network as our ground control for communications, at their standard 19 kilowatts array, we would be getting 75 kilobits per second uplink to the satellite, while at Earth going down to 20 kilobits per second at Venus. And this is enough for course correction or software update along the way. However, once we actually arrive at Venus, our downlink rates would fall to 14 kilobits per second, meaning that any data accumulated would have to wait a generous amount of time to be compiled at Earth, and would require some amount of patience from scientists on the ground. Lastly, the final major system I want to talk about is the temperature control system. Of course, when you're 25% closer to the sun, passive control isn't going to cut it. The spacecraft would melt fairly quickly. We also wanted to avoid pump action cryocoolers in order to maintain temperature, as those create excessive noise on camera instruments and spectrometers, especially infrared spectrometers. And we wanted to maximize resolution as much as possible for that. In the end, we selected a conical rotary screw design being developed by Vert Rotors, which very comfortably fits the CubeSat volume and mass constraints, as seen by the credit card being demonstrated to scale in their diagram. And they would be able to keep all the instruments within operational range for an extended period of time. as well as creating virtually no vibrations. So now that we have the full working TUCAN design, what are we left with for the science? Approximately 4 kilograms of mass remain in the mass budget, with 4 units of space for application of scientific instruments. We also have high flexibility in terms of they can be placed on any face of the CubeSat you desire for either Venus spacing observations or orbit normal observations. We would be able to dedicate up to 300 watts if necessary between communications periods with 3 microcontrollers working in parallel for processing needs. So what science should we actually do while we're there? VEXI, the Venus Exploration and Analysis Group, defines scientific goals that would help to answer questions existing about Venus and phenomena around there. We selected 2 of these, being the superrotation of the atmosphere and the ionosphere hole anomalies. And as a sample mission, we have determined a few instruments which could be used to analyze those and what kind of data return you can get. To begin the lower atmosphere study, the phenomena of superrotation, as we've just heard a little bit about, is an interesting anomaly where the lower atmosphere rotates 60 times faster than the surface. And in order to study this and provide explanations on why this occurs, observations would need to be made to categorize atmospheric temperatures at those altitudes, wind velocities, and vertical composition profiles. The Argus IR spectrometer, an instrument which is actually flown already on CubeSats for Earth-based observation, would be able to answer a lot of these questions while fitting within our mass and power constraints. Its operating range is from 1 to 1.7 microns, which means we would be able to get the following altitudes from 0 to 80 kilometers approximately during night and day cycles, depending on the local atmospheric temperature. And that would allow us to make a dynamic map of the atmospheric conditions as we orbit Venus and see what's actually going on with the mesosphere to lower troposphere. As for the ionosphere hole investigation, this anomaly has been detected by previous Venus spacecraft, specifically, I believe, Akatsuki and the PVO and VEX missions, where holes appear with borders of 10 to 50 nanotesla in the ionosphere on Venus's night side, where no magnetic field is present at all. So several theories already exist that attempt to explain this phenomenon, most of which rely on the interplanetary magnetic field interacting with Venus's ionosphere to produce these holes, and several of them imply correlation with high solar wind activity. So in order to analyze what's going on there and to put these theories to the test, we've selected the NSS magnetometer and ion neutral mass spectrometer, both of which also have flown aboard Earthbound CubeSat missions. These would be able to provide us with a lot of relevant data for this. Namely, the magnetometer would be able to characterize the holes and determine their locations, sizes, and periods of appearance. And the ion and neutral mass spectrometer would supplement this by characterizing the ion environment around Venus and correlating it to levels of high solar wind activity. This would corroborate the data coming from the magnetometer to provide us a good model of what's actually going on with Venus's ionosphere. So that concludes the sample science mission that we've determined aboard TUCAN, and one example of many options of what it could potentially do after independently traveling to Venus. So what's our biggest challenges at this point with this sort of mission design? Of course, a lot of these instruments are not designed for the very intense Venus radiation and thermal conditions. Their lifetimes would require validation testing, particularly for the batteries and the propulsion systems, which would be undergoing unprecedented levels of activity and load. The power management systems would also have to be upgraded to allow each of the systems that we have modified for additional power usage to function at those higher levels and to benefit from the extra incoming power. As I mentioned, we are not satisfied with our communication solution and are looking for better options, whether it be a better satellite to include aboard the CubeSat or some sort of better ground-based Venus tracking system. And finally, the attitude determination control systems available for CubeSats currently do not have the software necessary for interplanetary travel, as they don't have interplanetary navigation solutions. Unless there's something I'm unaware of, this would have to be developed in time for a TUCAN mission. And finally, I want to talk about the benefits that TUCAN provides. After seeing this analysis, you see that a CubeSat has the potential to travel to another planet, whether it be the Moon or Mars, Venus. In the future, we hope to do analysis to see whether an upgraded platform could even make it as far as the asteroid belt of Jupiter and its moons. And it has the capability to perform some level of science there. This means that we could potentially be opening up the solar system to smaller non-government space agency teams looking to do interplanetary research. Finally, in terms of launch opportunities, this would be a secondary payload. We imagine it leaving from LEO, as I've mentioned, but that would mean that launch opportunities occur almost whenever the synodic period occurs between the target body and Earth. In Venus's case, this is every 540 days approximately. You'd be able to begin your mission at those intervals without having to wait for either the appropriate launch vehicle to come along that can take you there, or the necessary gravitational windows. Now, of course, in a mission that desires to use more space for scientific instruments, or just make it there in a shorter period of time, we will be conducting analysis on gravitational boost windows that could be used to minimize those factors in reaching another planet. But at present, our analysis stands as a way to demonstrate that even on the most basic trajectory, TUCAN is able to achieve science at Venus. And that is the conclusion of our analysis. Thank you very much.
Any questions?
You said that interplanetary navigation is a challenge, but what are your plans for that? Do you want to develop that by yourselves?
So to answer that, the Drexel Space Systems Laboratory is currently working on the architecture for the platform itself. We did not have a specific scientific mission selected, and are willing to host other payloads should a relevant or compatible mission come close.
Have you already designed the deployment mechanism of the antenna that you will need to communicate with Earth?
We've been looking at, so you're talking about the CubeSat stuff?
Yeah.
We're looking at a model based on the Ionosphere mission antenna, which is an unfolding parabolic dish with a mesh dish for the receiver. And that is the basis of the numbers that we have here. The analysis can be seen there.
What are the dimensions of that dish? Because
it's approximately, I believe, 50 centimeters in diameter.
okay, thank you.
I'd like to add that fits within a 1.5 U volume. We do have the space to allot a little more volume to it, so we want a bigger dish. But as I said, we want to maximize off-the-shelf components and the system that is already designed.
Any further questions? Yeah.
Right. So I think at the beginning of the talk you mentioned the price of something like 10 million for the mission.
Yes.
Is that right? Yeah. And then you also mentioned the fact that you would need to probably do lots of requalification of certain systems. So is this price of 10 million including those requalifications that you talked about?
Yes, absolutely. So this price includes all of these mentioned components, the launch vehicle, and the necessary amount to pay to get aboard that launch, and additionally, well, with the amount that Drexel Space Systems Laboratories provides, validation will be practically free. So that's a joke. I do mean that we'd be performing validation for these components in-house and assembling it at Drexel.
Any further questions?